Hi, I'm Gaston Fermandois from Santa Maria University in Santiago de Chile. The title of this talk is Client-Server Coordination in Real-Time Hybrid Simulation Testing. Let's begin. Real-time hybrid simulation is an experimental method for dynamic testing. A structure is divided in two components, a critical element which is tested in the laboratory, meanwhile the rest of the structure is simulated numerically. The interaction between both substructures is enforced through the use of actuators and sensors. It provides a realistic and cost-effective way to study structures compared to shake-table testing and other pseudodynamic methods. One of the challenges of RTHS is the coordination of finite element analysis software to provide more realistic analysis of the structure. So for finite element analysis, we usually would like to include three-dimensional models and structures that have nonlinear response. And this is quite difficult to consider in the real-time hybrid simulation framework. So the objective of this study is to provide a reasonable procedure for researchers in RTHS to achieve the coupling of widely used finite element software with control software available in the laboratory. In this study, we propose a client-server virtual real-time hybrid simulation platform. The platform is illustrated in this figure, where we can see different components of the client-server communication protocol, mainly a layer that will interact between the numerical substructure finite element server and the Simulink client, which will run the control algorithms for RTHS through a gateway called OPF Connect that comes from OpenFresco. Additionally, we can enable other servers. For instance, in this case, we have a specimen that is also modeled using a finite element software like OpenSees, and we can create the communication using another interface called generic client. Also important is to consider that both the numerical substructure and the Simulink client, the control algorithm, will run at different rates. So a multi-rate transition task is included in order to go from a slow speed simulation rate to a fast speed simulation rate in the Simulink client. The following numerical example is considered to validate this framework. A four-story reference structure is considered where one bay of the first story of this structure is the experimental substructure, meanwhile the rest is the numerical substructure. We consider nonlinearity for the structural elements. In particular, we consider a steel material with isotropic strain hardening, and the natural period of the structure is 1.9 seconds. The whole framework and its implementation is available at a GitHub repository that is available for the community to work with this example and learn from our development. The main results of this study are shown in this figure, where on the top figure we can see good synchronization between the target and the measured signals with a J2 performance indicator of less than 1%, which it's quite good. And on the bottom figure, we can see a very good agreement between the response of the reference structure and the measured responses from RTHS, which indicates that this test has very good reliability and is quite realistic. Regarding the lost data from this soft real-time system, we plot the mistakes at each time step. We conducted 40 simulations to study the variability of the mistakes, which is a function of the load on the CPU of the computer that is running the test. And we can see that from 0 to 4 seconds of the simulation, we see the maximum number of ticks or data loss, which is not going to be higher than 426 on average. After the 4 seconds, which we assume to be the initialization of the software, we can see that the mistakes or the missed data will not be higher than 20 ticks, and this will be a function of the task that the server or the client are running at a particular time during the integration. So in conclusion, we proposed a framework for client-server virtual RTHS. It is validated through numerical simulation, and we successfully demonstrated how to use this communication protocol to interact different software for more realistic analysis. The authors anticipate that this work will boost the development and deployment of real-time hybrid simulation with high-fidelity numerical models. Future work will consider the implementation of this CS method in real-time hybrid simulation over a network of dedicated microcontroller clients, for instance, the Space Microlab box or a Raspberry Pi, and finite element machine servers in different computers in a laboratory setup. With that, I would like to thank you for your attention. If you have any questions, you can reach me by email or through Twitter, and you're also invited to visit our website. Thanks.